So good morning, everyone. I am Sylvain Boj. I'm the manager of a small company based in Bordeaux, in France, and we are manufacturing scientific instruments, as the one you can see in our lab. Today, I'm going to talk about characterization of nanoparticles, mainly about the size of nanoparticles. So, in order to organize my presentation, first I'm going to give you an idea of what is dynamic life scattering. Okay? Then I will start to explain more in details what we are doing for anisotropic nanoparticle, which is something which is brand new. And after that, I will end with some presentation of some very specific tools that we have developed for using our instruments coupled with the big instruments such as here some beam lines in SOLEIL. Okay, so okay, so first thing, why it's important to measure size of nanoparticles. So I think that you already know a bit about that, but it's really important. It's the very first characterization of nanoparticle, meaning that when you know the size of the nanoparticle, you can really know if your nanoparticle is able to penetrate into the membrane of human cells, for example, for specific vaccines or these kind of things. Or you can have some functionalization, some properties of materials coming from the nanoparticles. So all the size is really related to the very first knowledge, the very first characterization you have to know on nanoparticles. For this, you have many techniques that exist today. So we have been discussing about transmission electron microscopy, so which is a very common technique. You have heard about this, I'm sure. After that, you have more older technologies, such as the differential centrifugal sedimentation, all this kind of old technology based on mass. And you have, after that, the size. You have received a very good training about size here, so you know exactly what we are talking about. And on the optical side, you have particle tracking, laser diffraction, and dynamic light scattering. So dynamic light scattering is a small instrument, first thing we need to do. And in the future, when we're going to work in a lab, we will see that as soon as we're going to touch nanoparticles, we will have a DLS, what we call a DLS, which is this kind of instrument in the lab. It's a really common instrument, okay? So now we're getting a little bit into the physics part of dynamic light scattering, just try to explain you as much as I can. Okay, so first thing, we are measuring nanoparticle size when they are into a solvent, what we are calling a colony, okay? So we are using the volume motion of the particle. So you know what is the volume motion. The solvent, the temperature, is going to move the particle. We used to say that the particle is a little bit moving like a drunk man. So it's going one way or another, and it's going a specific distance, okay? In the beginning of the 20th century, a French mathematician, Bachelier, has shown that the square average of the average of the square distance is linked to what we call a diffusion coefficient, to this calculation. Okay, this diffusion coefficient is a kind of speed of diffusion of the particle into the medium. If this diffusion coefficient is big, you can see that the particle is going to be spread into the colony. If it's d is small, the particle are not going to be spread very far. Okay. Few years later, Einstein has found this formula, a very specific formula, what we call the Stokes-Einstein formula, linking this diffusion coefficient to some physical parameter of the colony, such as the temperature, the viscosity, and the diameter of the particle. So, just to understand very clearly, you can see that if the temperature is increasing, then the diffusion coefficient is increasing, so the particle is going to make a long distance in the same amount of time. If the viscosity is, or if the diameter is big, the diffusion coefficient will be lower, so then the particle is going to make a small distance, okay? Same thing for the temperature. If the temperature is high, I told you already, and if the viscosity is high, for example, then you will have a small diffusion coefficient, so your particles are not going to move very far. So you understand that this diffusion coefficient is really linked to three parameters, which are temperature, viscosity, and diameter of the particle. So the idea is quite simple for DLS, is if we find a way to measure the diffusion coefficient, knowing the viscosity of the colony, knowing the temperature, we are able to go back to the diameter of the particle. Okay? So this is the main idea that you need to know. First, you need the Brownian motion, and you need to follow this kind of equation. Okay? So for that, now the problem is just to find an experiment in order to measure the diffusion coefficient. For this, what we are doing, we are launching a laser into the colloid here. The particles are going to scatter the light coming from the laser. We are collecting the light in a detector. Then we are going to have a signal processing doing an autocorrelation. I will explain why. And then we are going to have a data analysis, and through that we can come back to the size of the particle. So just to understand why we are doing an autocorrelation here, just try to understand clearly. Maybe the next slide will be easier to understand. So first thing is that autocorrelation is not something which is very famous for you. I'm not so sure, but if we do an autocorrelation of images, it's something which is clear for you. Imagine that we have two images and we are going to do an autocorrelation of two images. If they are exactly the same, you have one. It's fully correlated. If you are comparing two images which are completely different, you have zero, no correlation. Okay? So now imagine that we are looking at a garden with kids playing in the garden. I'm taking a picture of this garden every second. And I'm comparing all the pictures to my first picture. Then let's assume that the small guys are going to run very fast, and the bigger one are not going to move so fast. What is going to happen? When I'm going to compare the 1 second with the very first one, I will see that they are really correlated. So it's nice. But if I'm considering only the small guys, after a few seconds, I will not be able to find them again. So I will not have any correlation between the two images. Okay? So you can see that I will coming, if I want to have a graph, I will come from high correlation to nothing very quickly. If I'm considering now the big guys going very slowly, then the correlation will stay for a longer time. So then I will still, at the end of the day, will have no correlation between the beginning and the last picture, but my autocorrelation will go slowly, will decrease very slowly. So now you can understand that this autocorrelation is really linked to the size or to the movement, the Brownian motion of the particle into the colloid. Okay? If the particles are small, if the viscosity is low, if the temperature is high, then your particles are moving very fast. You are going to decorrelate very quickly. If you have a high viscosity, low temperature, big particles, you are going to decorrelate very slowly. Okay? So after that, this is just to have an image. Okay, I think it's important. After that, physicians have done some calculation, considering that you have a coherent light scattering on the different particles here. Here you are gathering all the interference pattern coming from the different scattering light. You do all the calculation, it's mathematical physics, you do this, and you found that if I'm considering the autocorrelation, which is this kind of function, this is a normalized autocorrelation, then my autocorrelogram will be this kind of equation, which is an exponential decay. And the thing which is really interesting is in that exponential decay, I can see my diffusion coefficient appearing here. Okay? In the relaxation time of my exponential decay. So now it's very clear that if you have a very high D, you remember D is linked to the distance done by a particle, okay, in the same amount of time. So if you have a high D, meaning that this will decrease very quickly, so your autocorrelation will decrease very, very quickly. High D, small particles, okay? If you have big particles, it's going to be a low D, so in that case, in small d, in that case, your decorrelation will decrease very slowly. Okay. The thing which is really good, if you have all the parameters, which is angles of scattering light, the index, refractive index of the solution, the wavelengths of the laser, if you have all these parameters, viscosity of the solvent, temperature, all this, you can really just trying to fit this equation by experimental data, you can find the size of your nanoparticles. Okay. So this is really the problem we are facing now. Meaning that here it's the same, it's a logarithmic scale. That's why you will not see this relation classical exponential decay. It's an exponential decay, but with logarithmic scale. So here you have an exponential decay, and the problem now is very simple. I have an exponential decay. I know that this exponential decay has this shape, and I need to find the good diffusion coefficient in order that my theoretical curve fit the experimental data. Okay. For this, we are going to use algorithm, mathematical algorithm. That's why DLS is not so easy. It's a cheap instrument, not a big one like here in SOLEIL. It's a small one that you can find in every lab. It's not very expensive, but the problem is that it's quite a little bit complicated. Why? Because first, we need to make some chemistry in order to have a good query. Second, you are doing a physical experiment with a laser, and you need to see absolutely this autocorrelation, so it's nice, it's clean, and you can get information from that. And then you need mathematical algorithm in order to fit one curve to another, in order to find the good diffusion coefficient. Okay? But if you do it properly, you will get very good results. So then, okay, coming back to the Stochastic equation, you can find the diameter. Okay? So we are using, so now let's talk about the mathematical algorithm. We are using, in fact, three different algorithms. The first one, cumulant, is the one, it's the standard. So in every machine, you will find it. Cumulant is assuming that you have only one monomodal distribution, meaning you have only one size with what we call a standard deviation. So it's a statistical distribution, normal distribution. And cumulant is assuming that you have only one size. Okay? It's very strong, it's very famous, and when you are going to publish some scientific papers, everybody will ask you for the Z average and the PDI in order to know what you have in your coloring. Okay? But it's not the best one for sure. Because when you have a polydistance coloring, which is most of the time what we have, in that case, it's not going to fit properly. Then you have Padé-Laplace. Padé-Laplace is an algorithm coming from the École Normale Supérieure de Lyon. And Padé-Laplace is assuming that is using Laplace inverse calculation, and is assuming that you have a discrete, multimodal discrete distribution size. Okay? So Padé-Laplace will give you, do you have three different sizes, 3, 4, 5, or 2 only? Padé-Laplace will give you this information. And the best one is SBL. SBL is a continuous multimodal distribution. So, and will give you the best information that you can have. Okay? So just to give you an example, here we have mixed 30 nanometers particle and 200 nanometers nanoparticles. Okay. Cumulant will give you a big peak in the middle of these two values. Okay, because cumulant is not able to see population. Padé-Laplace will show you two peaks telling you, okay, you have two population, main population in your sample, so you need to take care of that. And then SBL is going to make a really nice. Okay. We are using these three algorithms. Why? Because you will see when you are making a lot of measurements, sometimes it's difficult. Sometimes one algorithm is not going to fit very well. You need to use the other one. So it's always good to have many mathematical algorithms in order to find a good solution to your mathematical problem. Okay. So this is the way we are measuring our nanoparticle. So first thing, you have what we call a timeline. This is the photons coming on your detector. So we are gathering all the photons, and we're doing a autocorrelation on all these timeline. This is 45, 50 seconds, for example, as an example. Okay. So first thing, you find this data, you know, the blue dots. Okay, the blue dots are the experimental data that we are getting from the detector, from the autocorrelation function. Okay, they are here. We take these dots, we put in the algorithm, we find this size distribution, showing here that we are nearly 4 nanometers average here, and the standard deviation, which is here, standard deviation of 27%. Here, it's a standard deviation of this distribution. It's a monomodal distribution, so it's fine. And this is the result of the mathematical algorithm. Then what we are doing, we are imagining, if we are calculating, if we have this size distribution, what should be the autocorrelation coming from this size distribution, the theoretical correlation that we will have. It is for sure a decay like this. It's the green line that you can find here. So the idea, when you use a mathematical algorithm, you need to look if the mathematics have done a good job. For that, we are doing the difference between the theoretical data, which is the green line, and the experimental data, the experimental dots, which are the blue dots, okay? The yellow line here, it's what we call the residues, is the difference between the experimental data and the theoretical data. When you find that the residues are below 1% error, you can assume that, okay, mathematics is working well. You have reasonable results, and you can expect that the level is really good. Okay. So this is just to give you an idea of how you use DLS. Please, in the future, when you will be in a lab, I'm sure that you will be using DLS for sure, because the way to work on nanoparticles. Please always check the result coming from the mathematical equation. Because mathematics can tell you everything. They can give you very strange solutions sometimes. So you always need to check that it's well fitting the experimental data. So this slide is really important. Okay. Now I've been talking about dynamic class scattering, so it's a summary of what I said. It's really important because it's something that you may have in mind. So just to summarize, we are starting with the Brownian motion of particles in a solvent. We are looking at what we call a diffusion coefficient, which is a translational diffusion coefficient. I will explain why translational, you will see after that. We use Stokes-Einstein equations, and thanks to that, we can come to the hydrodynamic diameter. So physically, we are doing, we are launching a laser, and we are looking at the scattering light at a specific angle. We do an autocorrelation. Thanks to this autocorrelation, we find the exponential decay, we find the diffusion coefficient, and knowing the diffusion coefficient, we can have the diameter, knowing viscosity and temperature. Okay, so this is the way we are measuring size of particle using dynamic light scattering. Okay, so it's really important because now I'm going to explain you something which is a little bit more complex, how we can measure size of anisotropic nanoparticles. Everything here is related to spherical nanoparticles. Okay, so now let's jump into something which is more complex, but it's going to be nearly the same idea. That's why it's important. We're going to talk about diffusion coefficient, we're going to talk about autocorrelation, we're going to talk about all these items. So first thing, why nanoparticle shape matters? More and more, we are talking about advanced materials, which are new materials. Here you can have some carbon nanotubes for a semiconductor, or silver nanotube for very good electrical transmitters. Here you have a B pyramid. I don't know exactly what you can do with this kind of gold nanoparticle, but it's a specific shape. Even you can do some stars, nanoparticles. Now we can really control the shape of nanoparticles. And here you have a kind of virus, a very strange virus, with a few microns length and 100 nanometer width. So you have more and more, when we are looking at the very small environment, we are looking at anisotropic nanoparticles. Okay. Why they are important for the industry? Because with anisotropic nanoparticles, we are entering into a new world where we are, by combining different nanoparticles, okay, putting them together, making nanotubes or whatever you want, we are reaching new properties of materials, which are really, really important. So as an example, we are increasing the efficiency of a solar panel using this kind of nanoparticle. We have new optical materials. Okay, here, for example, by adding nanoparticle, by transferring the electrons, you have a way to improve the efficiency. So you need to have very strange nanoparticles with a specific length and width. And you have nanocrystals with the different growing nanocrystals. You have like this for imaging. So more and more, we are talking about new, what we call advanced materials, new materials coming from these anisotropic nanoparticles. So it's really time to consider these anisotropic nanoparticles and try to be able to characterize them. So let's consider the movement, the Brownian motion of an anisotropic nanoparticle. Okay, so here you have an anisotropic nanoparticle. So in fact, like my pen here, we can split the movement into two movements, even a little bit more, but let's say two movements. First one, your particle, like my pen, is going to move in a Brownian motion, but without any rotation. This is what we call the translational diffusion coefficient. Then after that, my particle can rotate. Okay, So this is the rotational diffusion coefficient. And if we are gathering the both, okay, so we will have my particle is going to move, and I can add a transactional diffusion coefficient and a rotational diffusion coefficient. Okay? So the main idea is that if I have two different diffusion coefficients, the transactional and the rotational, I will have two different movements leading to two different diffusion coefficients. So we need to change a little bit the experiment in order to see how we can measure these two diffusion coefficients. Mathematician has done a good job, and they have made a calculation of the theoretical diffusion coefficient, transactional diffusion coefficient, and the rotational diffusion coefficient. Okay, they found that it's more or less the Stochastic equation for anisotropic nanoparticles. Okay, it's really the same thing. You remember for the Stochastic equation, we have the diffusion coefficient linked to the temperature, the length, and the viscosity. So here, if you get rid of this, you have only this parameter. It's really the Stochastic equation. Okay. So what we can see is now they have done the calculation. They found that in fact this transactional diffusion coefficient is linked to the length and to the aspect ratio of the anisotropic nanoparticle. And the rotational diffusion coefficient is linked to the length by 3 and the aspect ratio of the nanoparticle. So the idea is exactly the same that with traditional D-DLS. If I have a way to measure the transactional diffusion coefficient and the rotational diffusion coefficient, I will have two equations, two unknown value, which is L and the length and the aspect ratio. Okay, I can do my calculation. I can find the length, the aspect ratio, and knowing the length, I know the width for sure. And I can come back with the length and the width of my nanoparticles. Okay? So now the problem is, can we measure the transactional diffusion coefficient and the rotational diffusion coefficient? Okay? How we can do that? So this is really new. It's famous. In theory, you have a lot of mainly Spanish researchers from Valencia has been working on this, and they have spread a lot of very interesting research, but it was only scientific papers. For the very first time, we have developed special instruments enabling to measure this kind of values. Okay. So what we are doing first, we are sending. D-DLS means depolarized dynamic light scattering, which is not a very good word because it's not depolarized. It's in fact, it's much more than polarized because we are using a very polarized light in order to do the detection. So depolarized is just saying that we are looking into another polarization mode. Okay, so let's say that. So you know what is the polarization of a light? It's the vector in which you have the electric field coming from lead to the photons to the light. Okay, so imagine here we are sending a vertical polarization light to the sample, and we are here splitting the light. It's vertical polarization. Here we are checking here the vertical polarization too. Okay, so vertical polarization here. So it's VV, vertical. Here it's VH because we are looking at the other polarization. Okay, so it's a vertical horizontal like here. So we are splitting, we're gathering, we are detecting these two polarization modes. Okay, I will explain why. So let's try to understand what is happening for the matter, for the nanoparticles. So first thing, so the polarization vector is here. Okay, you have a light here with electric field coming into the particles. Okay, when the particles are spherical, what is going to happen? All the electrons that are going to meet this electric field are going to move vertically. So they are going to scatter the light vertically. Okay, so VV is going to show a very good result. When you do traditional D-DLS, it's a VV D-DLS in fact. Okay, but the thing that you can see that if your particles are really spherical, okay, if there is no constraint, the electrons are going to move this direction. So okay, so in that case, you will have only vertical information here. So you will have the scattering light will be on the vertical polarization, and you will have nothing on the horizontal mode, nothing. Okay. if now you have an anisotropic nanoparticle, let's say that these arrows are an anisotropic nanoparticle, we can assume that these particles, because of the anisotropy, are not going to move in that direction by the incident light, but are going to move according to this direction, which is the more probable movement for them. So what is going to happen? First thing, the incident light is going to excite these electrons into that direction. So you need to do the projection here and you will have the value. And if the particles are moving this way, in that case, you can see that you will have some information on the VH, on the horizontal scattering line. So the information now is clear. If you have a spherical particle, if you have the incident light coming on the spherical particle, you will have nothing on the horizontal detection. If your particles are anisotropic, in that case, you will have information on the horizontal. You will have at least some photons coming on the detector on the other horizontal polarization. Okay? So first thing, we have a way to know if the particles are anisotropic or not. And it's working very well, I can tell you. We have done the check many times. When we are spherical nanoparticles, nothing on the horizontal polarization. As soon as you put some anisotropic particles, you have a lot of photons coming on the detector on the other horizontal polarization. Okay? Nevertheless, physicians, mathematicians have done the calculation and they found the following. If on the VV side, I'm doing an autocorrelation, I will have this kind of autocorrelation. I will have 2 exponential decay. And if I'm looking on VH, I will have 1 exponential decay, okay, for an anisotropic nanoparticle. And the thing which is interesting, you can see, is that the very first decay here, the very first time relaxation, is linked to gamma T, which is the translational diffusion coefficient, and the second part is linked to the rotational diffusion coefficient. The second relaxation here is linked to only the translational diffusion coefficient. So at the end of the day, if I'm looking at anisotropic nanoparticle, I may find 2 different relaxation. In another word, for me, it's 2 sizes of particles, because you remember for isotropic particles, if you have 2 relaxation, meaning 1 relaxation is 1 size, so if you have 2 relaxation, it's 2 sizes. Here you will find 2 sizes, which are not sizes. It's just linked to the rotational and translational diffusion coefficient. So now we have a way, making the autocorrelation on VV and on VH, to have the information about this value, which is the time of the relaxation, the mixed relaxation of translational diffusion coefficient and rotational coefficient, and we can have only the translational diffusion coefficient. So you can see that if we do properly the measurement, we have access to this value, so we have access to this value and this value, and we have access to this value, so this value. So at the end of the day, if you have access to these 2 relaxation times, you will have access to the translational diffusion coefficient and to the rotational diffusion coefficient. Okay. So let's explain now how we can do it. So first thing, this is an experiment that we have done. Okay, you can see that on VV you have 2 relaxation, so 1 exponential decay plus another exponential decay. This exponential decay is linked to this value, and the other here is linked to this value. Okay, so the idea is the following. In order to be, okay, with 1 angle, I can make a measurement. If I have 1 angle, Q is linked, like for SAX, is linked to the angle of the scattering light. Okay, with 1 angle, I can have an information, but what we have seen is we need more angles in order to have better precision on the calculation on the length and on the width of nanoparticles. So the idea is the following. If I'm looking only at the translational and rotational time relaxation time here, if I'm writing this and doing this for different angle, this is a linear. I'm writing this on the graph according to Q squared Q. Then I will have a line, a straight line here. And this line, when Q equals 0, you will have 6 times the rotational diffusion coefficient. Okay? And the coefficient of this line is the translational diffusion coefficient here, as you can see. So it's quite simple. If I'm looking only at this, at the second relaxation, so I will see that according with the angle, with Q square Q, you will have a line going through the through zero. Okay, so and this line has to be parallel to the first one because it's the same coefficient. Okay, so at the end of the day, what we are going to find is to find one line here coming from this relaxation and the other line coming from the second relaxation. Okay, so when you are getting in the software, you have the choice in the software to decide, do you want to do SLS, which is statistic light scattering. It's a really static, not static light scattering for weight molecular measurement, all these kind of things. You can do traditional DLS, measuring the size of nanoparticle, and you D-DLS in order to measure length and width of anisotropic nanoparticle. Okay, if you choose the D-DLS, what is going to happen? So you are going to have VV and VH. So in the same time, we are going to look at the autocorrelation on VV and on VH. On VV, if it's anisotropic, I will have two peaks. You remember the two peaks showing two relaxation time, but this relaxation time is a fake one. It's just linked to the translational plus the rotational diffusion coefficient. Okay. And here on VH, you have only, you may find the same thing that this one, meaning the translational and rotational diffusion coefficient. So gathering all this information at different angles, now we can write the different lines that you have already seen. So let's have a look at the experimental results. This is what we have. So we find here on the second time relaxation, you find a line going through zero, which is working very well, and another one parallel to the first one, which is really related. So you remember that this distance is 6 times the rotational diffusion coefficient, and the coefficient of this line or this line, which are exactly the same, are the translational diffusion coefficient. Okay. So this comment is doing, you don't have to do just to put your comment inside, and you decide the number of angles you want to know and to measure, and then the computer will do the work for you. Okay. But it's important to look at this graph, because if you don't have this, meaning you have an issue. Okay, and it's really important. For example, if the second line here is going through zero, sometimes you can find it. In that case, the two populations that you see are really two spherical populations. If it's an isotropic population, you need to have parallel lines here. Okay, so that's why this graph is really important, because you can get a lot of information about what you are looking at. Even with this graph, you can see if you have a mix of isotropic nanoparticles, so spherical nanoparticles, and anisotropic nanoparticles. Okay, so let's now have a look on some experimental results. This is on nanorods, gold nanorods. So the first one, we have done some tests. So here we have measured at the TEM 47 nanometers, width of 26 nanometers. We are from 46, a little bit more in terms of width, but we have some explanation. I will give you some ideas later. What we have seen, for example, which is very strange, anisotropic nanoparticles seems to gather in a very specific way. They don't like to put that to be like this. They like to be in fagot like this. Okay, so we don't know really. And if they are like this, in that case, the width is increasing. Nevertheless, you have this. Here, another experimental results. So at TM, we have 28 nanometers and 14 nanometers on width. Here, we have, by our measurement, we have achieved 28.5 nanometers, so it's nearly the same, and 17 instead of 15, which is nearly we are really close. So it's working very well in that kind of sample. Another one, which is very nice, you can see the 10 images of this sample. Here, so we were measuring at the TEM 66 nanometers and 16 widths, and we have measured 17 nanometers, which is quite near, and 14 in terms of width, which is we have achieved nearly the good value. Okay, so just to say that if you compare DLS and SAX, for sure SAX is much more precise than DLS. Okay, but it's not the same machine. Okay, DLS is a small machine that you can have in the lab, and you cannot have this big SAX SOLEIL. You cannot get it in your lab. Okay, so you have some difference. Okay, but you can see that it's working quite very well. The theory is working very well. And that's it for the D-DLS and for all my explanation about depolarized dynamic light scattering. I hope I was not so boring. Now I'm going to explain a new development that we have done in our company on traditional DLS measurement, which is what we call the in situ measurement. Okay. It's more technical, a technical part. It's less theoretical, more technical part, so it's less boring, I assume. First, in many labs, what we used to do, we are taking the sample with a pipette, and we put the pipette into into a cuvette, and the cuvette, we put the cuvette into the instruments in order to make some measurement. Okay, and this is working very well. It's very good, and we are fine with that. But we have seen that there is a change of paradigm. Now, more and more people would like to see the size of the particle when they are in the reactor, in the synthesis reactor. When they are in the bottle, for example, if you want to see nanobubbles into a bottle under pressure, okay, you cannot sample because you need to be a few bars in the bottle, so you cannot make some sampling. So all these kind of things leading to bring now the instruments to the colloid and not the colloid to the instrument. Okay, so it was the main idea. So what we have done, we have developed what we call an in situ head. So you have two optical fibers. The laser is going, you have two holes here. The laser is coming from the hole in the bottom. And at 8 centimeters from this part, we can choose the distance, okay? At 8 centimeters from this part, into a small volume, we are gathering here in this hole, all the photons coming from the scattering light, from the nanoparticle, okay? So we put this in situ optical head. We plug this head into our instrument, and we are able now to make any measurement just having this little optical head. Even you can measure your coffee when you are taking a coffee. You just have to put the laser into your coffee, and you make the measurement in real time of the size of the nanoparticle that you have everywhere. So this box is 20 centimeters by 20 centimeters by 5, so it's very small. It can work and very low consumption. It can even work with a battery. So it's something that even you can bring on the field with you, okay? So the idea is that you have the light coming, and at 8 centimeters, we are gathering the light here, and we detect the light and the light coming into the optical fibers, okay? So the volume that we are measuring is a small volume. It's, imagine that we launch a laser into the input, and you put a laser on the output, laser output. So you can see here that we are studying a volume which is around 400 microns length, 100 micron width. This is the volume that we are measuring. So this is really interesting because you can put this volume here, but you can put this volume here near the glass, the bottom up. You can even make a mapping of the size of your colloid. Maybe you can have some differences in terms of size everywhere in the sample. So here, this is an example that we have done at the EMRCP in Toulouse. It was the synthesis of ibuprofen. So at the beginning, it's a double jacket reactor. We put our head here, we launch the laser inside, and at the beginning, we didn't see anything, which is normal because we have nothing. Then the very first nanocrystals start to grow. As soon as we have few nanometers, we were able to detect them. And then we have all the kinetics. In here, you can see in the logarith scale, we have all the kinetics of the particle going from nothing to nearly a few microns, okay, size, okay? The idea is that it's really simple to do that. And the only thing that we need is you need to have a transparent window in order to be able to launch the laser inside the colloid. You have something that I need to say. You can see on the rear that there is a stirrer inside. You need to stop steering when you are doing the measurement, because we are looking at the measurement of particles in a Brownian motion. If we put a special movement to these particles, okay, you will not be able to find the good size of particles. So we were obliged to stop steering, to wait a bit, to make the measurement, and then we start steering, and then we have the, okay? You have some parameters that you need to control. So here it's our traditionally, something which is very interesting is when you are using your nanoparticles, it's easy. You take your bottle, your vial with the sample inside. You just have to put the sample here in front of the laser at 8 centimeters and you make the measurement there. So it's very easy to make any measurement with any kind of vial here. You can have a big bottle, a small one. You can, even in a sacs, these very small sacs tube, we have been able to make measurements of nanoparticles. Here, it's coupling with a capillary. It has been done with a SAX instrument from Bruker. So you have the X-ray beam coming here, you have the capillary here, and at the same time, we send the laser inside the capillary, and at the same time, we were able to measure the size by SAX and the size by DLS. And the correlation between the measurement by SAX and by DLS was really perfect. We have done this with the University of Leuven in Belgium. Okay. What we have done here, we have a couple of stories with SAX, with Bruker, and with Xenox, you know, the famous, another French company based in Grenoble. We are working with them. And we have done some also coupling with the SANS, with neutron scattering, same thing. We are looking at the SANS, scattering coming from the neutrons, and at the same time, we are coupling with the light in the sample. So we make the measurement in real time at the same time. The reason why it's interesting to do that, it's DLS, it's easy to use, you can have any information, and SANS or SAX are more difficult to use because you need to have the slot, the good time in order to come here to make your measurement. So you can check if your sample is nice even before doing your SAX measurement, okay? Because DLS is quite cheap and easy to use instrument. We have coupled, for example, our in situ head with an Anton Parr microwave reactor, a synthesis reactor. So Anton Parr, they had a big machine, a big microwave, and this microwave allowed to make the synthesis of some nanoparticles, and they used to have a camera inside. We removed the camera and we have put our head here, and we have done another hole, and then we were able to measure during the synthesis process the size of the particle when they were growing. So more and more now we are really controlling the size of particle during the synthesis process. Here, this is an experiment that has been done in Bordeaux. It was an hyperthermia experiment, meaning that you have some magnetic nanoparticles into a magnetic field here, and we were able to see the behavior of the particle when we apply the magnetic field. Okay. So it's another example where you cannot sample your nanoparticle, you cannot put them into the instrument, but you are doing an experiment and you are measuring, when you are doing the experiment, you are measuring the size of the nanoparticle. Another example, which is very interesting here and more actual, is the measurement of attenuated viruses into a vaccine. This is a Sanofi vaccine. You have here the syringe, you have even the blister over, and we are sending the laser just in this small part, and we were able to measure this, where you can see around 20 nanometers. This is really the size of the attenuated viruses, and this is more the aggregates. And even we have shown that when you are not keeping the vaccine into a fridge for a long time, you can see that this size distribution is completely different. Meaning that if the vaccine is not good enough, you will have a big here distribution from 10 nanometers to more than 1 microns, easily. It's a wide distribution. Here we have coupled, I'm sorry, it's a little bit long, but you can see everything that we can do with this kind of instrument. We have coupled the in situ head with the supercritical CO2 experiment. This has been done in Australia. So here you have a 2 centimeters thick glass. You have 100 bars inside, so it's very high pressure. And controlling the pressure, you can control the nanobubbles, so you can control even the size of the nanoparticle that you are synthesized. So what we have done, people were just looking at the colors with the camera. We removed the camera, we have put our instruments, and we were able to measure the size of particle during the different step of the synthesis process. Into microfluidic channels, we have been talking about that. This is really interesting. Same thing, we are focusing the laser on the little channels that you can see, and we have shown that it's working very well. We are able to measure size of particle even into microfluidic channel, and we can check the different place into the channel to see if the size, if the mix is going well, if the synthesis is well or not. That's it. So now just the sales part. You're not going to buy anything from us, but it's okay. Just this is all the instruments that were manufactured in Bordeaux. So you have traditional Vasco, which is a patent coming from the French Institute of Petroleum for dark petroleum. We have the Zeta Potential Wallis. We have the in situ head with the Vasco Keen, which is really dedicated to kinetics, to measurement mode outside of the box. You have the Amerigo, which is a mix of DLS and Zeta Potential, and you have the Tetis, which is the very new one, enabling to measure anisotropic nanoparticle size. Okay, and that's it. Thank you very much.
Thank you very much, Sylvain, for the very interesting presentation. I believe we have some questions now. Everything was clear.
Thank you for such an interesting talk. Just to understand correctly, one of the main difference from the normal DLS and the depolarized DLS is that you can see the difference if it's a spherical particle or an isotropic. And this is based on the fact that you can have horizontal polarization.
Yeah, we are sending a vertical polarization in the sample. In a traditional DLS, you send a polarized light into the sample, and at a specific angle, you just detect the photons. That's it. Okay? Most photons are keeping the same polarization. When it's spherical particles, it's exactly the same polarization. Okay. Here with the D-DLS, for the experiment, the difference is what? Is that we are looking at the same time, we are looking at the horizontal polarization. You can see in the, we have the apparatus is showing that we are looking at the vertical polarization and at the horizontal polarization. We are looking at both polarization, and we got the information from both polarization. Okay? And the idea is, first thing is that when you have spherical nanoparticles, you don't have any photons coming, or very few photons coming on the horizontal polarization. As soon as you have an isotropic nanoparticle, you find a lot of photons coming on. So first, you have a way to detect if you have anisotropic or not, or spherical nanoparticles. But more than that, we are able, thanks to some good calculation, we are able, and good mathematics, we are able to come back to the size, to the length, and the width of nanoparticles. For sure, all the model that I show you, all the calculation has been done on cylindrical nanoparticles. Okay, this gives us, we have seen quite a good idea of what we have. Nevertheless, if you have other models that we are going to compute, actually, we are working on them, such as ellipsoid nanoparticles, such as plate nanoparticles, which is spherical but like a plate. Okay, these nanoparticles. We have all the kind of anisotropic nanoparticle, and you have different models that you can use. For the moment, the cylindrical model is what we work for most anisotropic nanoparticle. At least it gives you a good idea. The difference with SAX is very important. I just want to precise because I have seen the presentation from this morning. SAX is much more precise. You have seen SAX is touching the angstrom size. Okay, we are not doing this. We are just keeping at the nanometer, few nanometers. That's it. Nevertheless, we are not so precise, but when we have polydispersed samples, we are able to measure them. We have seen when we have a lot of polydispersed, we can measure. And it's cheaper. It's really and smaller. So it's really an instrument that you are doing. But you will see in your career, for sure, you are going to work on nanoparticles. I'm sure because it's really where the world is going now. So you will be working on nanoparticles for sure. So DLS is not the first time that you will hear this word. You will hear it a lot because it's something really important. Because it's easy, it's cheap, you can make some measurement and you can get really good information at the beginning, at least for the very first sample that you need to measure. Okay? Even it can be a good instrument to prepare your sample for then going to the SAX to make a very precise measurement. You see? So just to be sure that it's really non-dispersed, that you have done a good job, you have good filtration, your protocol is good, so you can test, and as soon as you have a good DLS, then okay, you can go to the size and you will see more precisely the size and parameters of your nanoparticle. But I don't know if with the SACs we are really able to, I think maybe we need to see that, but maybe there are some papers if you are able to measure anisotropic nanoparticle. I'm not so sure that they have, I don't know exactly where we are. Yeah.
I know that there are different particle sizes instead of fluids. So when I want to measure with DLS, I will face with a problem that the bigger particles have overlap with the small particles.
Yeah.
So we cannot measure the small particles such as with this DLS readings. So I wanted to how we can use this type of DLS to measure the particle sizes in fluids. And another problem that we face with when we have bigger aggregations, they tend to sediment.
Yes.
So they don't move in the solution. So we have to I don't know what we should do, but we have a problem to take the measurement of the size.
Yeah. Okay. So for the first your first question related to the mix of small and big particles.
Yes.
Okay. What you may have to know when you look at the theory of scattering light is that if I am considering particles having 10 times difference in terms of diameter, the light coming from the bigger one, 10 times bigger, is 1 million more than the light coming from the small one. Okay. Small particles are slow, are not really efficient in terms of scattering the light. Big particles scattering much more the light. Okay. So if you have a mix of small nanoparticles and big nanoparticles, for sure, all the light is coming from the big particles. And this is due to physics. You can jump, you can do whatever you want. You cannot change that. The only way to change that is your preparation protocol. You need first to centrifugate, for example, to solenoid, to filter, and you need to, if you want to see only the small one, you need to have a better preparation of your sample in order to be able to see the small one. Just to give you an example, if you have very small nanoparticles, but few mixed with a lot of big particles, DLS is not able really to see the very small nanoparticles. If you are considering only this sample. For this, you need to establish a protocol to avoid the big one if you want to see the small one. And you have many things. You have a simplification. Many simplification is good at the beginning, then filtration. You have some filter you can go through, and many times filtration and working again and making some measurement every time. The way to do a good DLS measurement is that you do a protocol on your sample, you make a measurement. You change the filter protocol, you make another measurement. You do it many times, and when your results are always the same, okay, you have reached the level of what you can do with your phone. Okay. For your second question, it was for sedimentation of this kind of things. Okay, so it's really important. Particles has to be for DLS in the volume motion. So if the molecular weight of the particle, or the mass of the particle, or the density is really high compared to the solvent, in that case, for sure, they will sediment, they will drop down, they will not have any volume motion, so you cannot do it. Okay? The way you have ways to have better efficiency is you can change the viscosity of your fluid. For example, you can have something, I don't know, because but if you have high density particles with a high viscosity colloid, in that case, your particle can go back into volume motion. Okay? So it's all these kind of things that you need to deal with. Okay? But for sure, when you have a sedimentation, we have a lot of experiments on this, you don't have a nice hologram. In fact, for DLS, at the beginning, you need to have a nice hologram. As soon as you have a nice hologram, that means that the experiment is working. Now you can go to the mathematics. Okay? But if the hologram is not nice, okay, don't go anywhere. And for sedimentation, your hologram is really a mess.
Thank you.
Yes?
So in that same like questioning, you have a lot of interferences with sample matrix stuff.
So I don't hear you very. I'm sorry.
And you have some interferences maybe with the sample matrix. What kind of interferences do you see?
What we see in terms of the sample matrix of a particular.
So if you have so particles of different types, so if you have different colors or anything like that.
It's not issue. It's the only thing is how the particle is going to settle the light.
Okay. So you don't see any absorption of.
Yeah, no, it's not a big issue. It's not a big issue. Except if all the light is absorbed. In that case, you don't have any scattering light, so you have some problems. You need to increase the power of the laser. Okay? So usually what we like for absorbing nanoparticles, we change a little bit the wavelengths of the laser in order to be outside of the absorption band of the nanoparticles. For example, for quantum dots. Quantum dots, you know, particles with a rare earth inside, and a small one, very small. And for quantum dots, the way to measure them, and we are able to measure them by shifting, we have even an application note that will send you if you want to see that. We have just shifted the laser wavelengths to the leading current. Usually, all this, I didn't say that, but we have seen we are working on the red laser, which is 635 nanometers. We have tested with the 780 nanometers, which is nearly infrared, and it's working perfectly because all the absorption bands are not so far from the visible band. Okay, so as soon as you are in higher wavelengths, okay, you are outside of the absorption band, so you have the scattering light, so it's easier to make solution. And we have seen that with the medium contact laser, it's working great. But if you have different colors, different shades, well, not different shades, but different colors, different composition, it's not a big issue as soon as your particle is set in the light. But it can be a problem because you cannot make any differentiation between the different nanoparticles. If you have different types of nanoparticles, with D-DLS you cannot make really difference.
Okay, so you did have like organic matter, maybe like
yeah,
particles.
You cannot make a difference only by size.
The capture index of the container measurement, because you saw that.
You are right. If the unaffected index is very high, then when you are seeing when the laser is coming, post laser, okay, so they can change the angle and they cannot meet exactly inside the curve. We need to take care of that. But the calculation we have done is that for many global glass that we have seen, quartz, quartz, all different glass that we have seen, is working very well. So the index is not so high, so we have such a problem. Not really. I said for the CO2 supercritical reactor, the thickness of the glass was 2 centimeters. As soon as we can get, so here for 2 centimeters, we need to take care about the effective index of the glass. Because for sure, if we don't take care of this, the two laser beams are going to meet inside the glass. So we don't have any volume motion, nothing. So you need to correct and do the good calculation in order to be sure that you are inside the code. But this is really easier calculation. It's not a big deal. But we are successful with we are actually, so what we are proposing is 8 centimeters because we are found it's quite easy to make measurement at 8 centimeters, but we are able to make more than 20 centimeters length. So we are really able to make measurement very far from the sample. But the main advantage is, for sure, I'm talking about the electrons and all this kind of, our customers, they really like the institute. One reason is that when you are preparing your protocol, for example, you prepare your sample, okay, you submit it, you do this, all this distribution and everything. You just have to take your sample, the vial, you put it in front of the laser beam, you make the measurement, and you have the result. Then you take your vial, you do things again, you bring back, and you make the measurement very easily. You don't have to use the pipette, to put it into a pipette, to put it into the machine, and then to start the measurement. It's really straightforward. So it's very cool, really. So don't forget, for D-DLS, you need to have to spend really good time into the preparation of your colleague. This is really important. You need to take care about the cologram that you need to find, you need to check that, please do it. Because a lot of the instruments don't check that. They just give you a result. Everybody used to say DLS is easy because you don't have a number. This is absolutely false. It's not true at all. You need to check everything. If you have a nice cologram, which is the cologram is really the representation, the physical representation of your particles. So you need to see. When you see the cologram, okay, you can play with the mathematics.
I have a question. Maybe it's another one because I'm not a scientist. But you say that basically we could use your DLS on any type of situation, it's very light.
Yeah.
Do you have any recommendation on the type of container that it's in? Because I suppose if it goes to something else that the solution you want to see, it should avoid any trace.
Yes, but it's easy because what you take your, you know that the head, you know that the point all along the laser. Okay, you have the head, you have the laser. The measurement is done 8 centimeters on the main face, and you have a very small volume that we are looking at. So as soon as you take the head, you put it in front of inside the colony, and different kind of profile. And even plastic one, it's not color, just transparent. And if you see that this meeting point is just inside, more than that, what do you do when we are just we go back to too much, okay? We are a bit busy, so what we used to do is we take our sample, we put in front of the laser, and if you don't see a cologram, we see the cologram in real time. So we have nothing on the computer, no cologram. I move and listen, okay, I have a cologram, okay, I'm inside. I know that I'm inside. You see, it's a really visual. You can really see when you are inside. Because otherwise you have no cologram. You don't have this shape, you have nothing. Okay, so yeah, sorry.
I also have questions, but also some of them are really with all these questions you have. Just I wanted to understand what are the sizes we can reach with this light scattering.
Yeah.
Exactly.
Okay, so
despite the fact that if you particles that are sitting, you cannot you can measure them, but you cannot reach the size.
Exactly. So the size, traditionally people used to say, so there is always a marketing coefficient on the size of nanoparticles, which is really fun. Because if you look at all the instrument manufacturer, they're going to tell you that they are measuring between 0.3 nanometers to 10 microns. The problem is 0.3 nanometers is nearly the size of H2O molecule, the water molecule. I have never seen a DLS able to measure water molecule. It's just mathematical calculation, so it's not true. The smallest size that we have reached is 0.8. But it's an experiment which was really difficult because you have no dust, nothing, and it was 24 hours in June. Okay? In order to avoid all parameters, we were obliged to average everything just to be sure that what we were seeing was really, and we need to make always a comparison between pure water and your colony, just to be sure that what you are measuring is really the effect of nanoparticle inside. Okay? So what we have reached is 0.8 with a quite difficult experiment, but this is what we have reached. We used to say that from 1 nanometer to 10 microns, it's okay. More or less, I prefer to say from 1 nanometer to 1 micron. Because from 1 micron to 10 micron, first, yeah, this is not so interesting. You have all the way to measure, you make the measurement. And after 1 micron, it depends really on the density of the material that you're using. For example, silicon nanoparticle, density is higher. So if you have silicon nanoparticle in water, after 1 micrometer, they are falling down. They are not in a normal motion. You see them. You move a little bit, it's white, you put them here, and a few seconds after that, it's completely clear, and you see everything as segmented. So it's not, so big particles, we can see them, but in specific conditions, they have to be in a Brownian motion. For example, at the ISMO, here, at the Institute of Molecular Science in Marseille, we have killed some bacteria. It was very interesting because the bacteria, they were swimming first. So they were swimming, so they were not in running motion, they were swimming. And we add some silver nanoparticles in order to kill them. And we have done the kinetic at the beginning, they were swimming, so no Brownian motion, no measurement possible. And suddenly we have seen a nice parallelogram. Okay, they are dead now because they are not swimming anymore. They are just moving into Brownian motion. And we're able to measure the size. Okay, so.
And I have a second question. I'm really impressed by the transportable laser. And you say that you can measure conditions about expansion of sheets.
Yeah.
But then the volumes are very small, so I'm wondering how it affects the quality of the measurement.
Yes, this is a very good question. It depends really on the volume that we are measuring. The traditional volume that we are measuring actually with the head that we have, it's really linked to the angle. Okay, if we are working at 170 degrees angle, so it's like this. Okay, so the volume that we are measuring is something which is 400 micrometers by 100 micrometers. Okay, if we want to go really in a microfluidic sheet, we need to decrease this volume because it's below that. So for this, we just need to increase the angle. By increasing the angle, okay, the volume is less, and by reducing the diameter of the beam. So all this we have done. We have achieved 50 microns diameter of the beam, and foreseeing at very 150 angles, we were reaching really small value. It was 80 by 50, 80 micrometers and 50 micrometers.
And then you have to count number to how many or just...
No, it depends. So the test we have done is on traditional nanoparticle with a good latex nanoparticle with a good scattering light, so it was okay to measure this. But after that, if your particles are smaller, if they are not really scattering the light, you just need to increase the power of the laser.
Okay.
You see, it's just a matter of, yes, increasing the power of the laser and waiting longer in order to get all the information and to average all this in order to have a good parallelogram. The main question is always to find the good parallelogram showing really the size of the particle.
Yeah. And then, in case of combining on the night,
yeah.
Your head able to support the vacuum? Or
yeah, completely. Yeah. We have two heads working at the ELL in Grenoble. And even they are in cross correlation between the two heads. So we are working with these guys, and we even with the science in Grenoble, we have done some experiment. I think they have one instrument, if I don't remember. So even in a radioactive chamber, they are using it. It's really passive because everything is through optical fibers. You have nothing inside of it. You have no electronics, nothing. It's just a block of it's just lenses and optical fibers.
Yeah,
and all not no, because the lens are silica, they are not moving. So we need to check that. We need to check that. I don't see a big issue with this. I don't see a big issue, but we test it.
Thank you very much.
Okay.
Thank you very much for
You're welcome.
time.